guys, in this tutorial we will go over the basics of decision trees. Before we start, please, if you find value out of this video, like and subscribe. Also, the links to the notes that you will see in this tutorial and the code that will be presented later on can be found in the description box. That being said, let's get to it. Introduction to decision trees. Decision trees is a very fundamental machine learning algorithm. Okay, fundamental machine learning algorithm. The reason why I emphasize on that is because there are several algorithms that are built on top of a decision tree. Okay, so the purpose of this tutorial is just to give you an understanding and a very high level view of what a decision tree is, how it can be applied, and how you can build decision tree models on your data set. Okay, so let's start with the introduction. So decision trees are one of the most intuitive and interpretable machine learning algorithms. Okay, they can be used for both classification and regression tasks, and that's a very nice feature. Okay, so you can use your decision tree for classification purposes, right? Meaning that if you are trying to classify observations into a specified number of classes, you can do that with a decision tree. Or if you are working in a task that has to do with predicting a number, you can use a decision tree as well. The main idea is just to split the data recursively based on feature values that lead to the most pure subsets. Okay, so what that means in plain English is the following. So the idea behind decision trees is to split up the feature space into rectangular areas, so that you ended up with, in the case of classification, you ended up with areas that are dominated by one specific class. Or in the case of regression, you ended up with the area that has a small mean square error, for example. Okay, but at the end of the day, it's just, given that you have a feature space, you want to split it up into rectangular areas. Once those areas are defined, then you can use that model, or you can use those areas to make a prediction or a new observation. Okay, that's basically the idea behind decision trees. Now let's go over section 2. How do they work? Okay, or how they work. A decision tree recursively divides the dataset into smaller subsets based on conditions on input features. Then each node in the tree represents a decision rule, and each leaf node represents a final output. Okay, so before I clarify the difference between decision node and leaf node, so let's take a look at this decision tree. So this is one of the reasons why decision trees are very popular. Okay, not only because they are flexible in the sense that you can apply it on classification and regression, on top of that you can visualize the model. Not only that you can visualize the model, but the model can be visualized in this particular fashion. Okay, so when you look at this chart, so it has a very natural flow built in. Okay, and the flow goes from the top to the bottom. So at the top you have what is called the root node. Okay, that's where everything starts. Okay, and when it comes to decision trees, it's gonna be only two options, right? Depending on what the rule is given at that node. If that rule happens to be true, then you go to the left, or if it's false, then you go to the right, like it's highlighted here, right? So, and in this case, what is the rule is if petal length is less than equal than 2.45. Okay, so if you're not familiar with the iris dataset, so that's a very well-known dataset in the data science, machine learning, and AI community. So it's a dataset that has 150 observations, and the observations are related to iris, and in particular they are related to 3 different types of iris flowers. We have the petal length, the petal width, the sepal length, and the sepal width. So we have 4 different measurements on the iris, and then the target variable is the iris flower, right? And then there are 3 options. There is versicolor, virginica, and I think setosa. So those are the 3 labels for the iris flowers: setosa, versicolor, and virginica. So the goal is, using the measurements on the iris flower, we want to predict the label associated to the iris flower. Okay, so this is a simple decision tree that in some sense use that data. We are trying to highlight how a decision tree works here. Okay, so then the rule is going to be shown at the very top. Okay, so then here is telling us how, or the percentage of the data that is being used, and the decision, right? So if this rule happens to be true, so then that means that we go to this node right here. So then basically the prediction will be setosa. So basically this decision tree is telling us that if petal length is less than 2.45, then it has to be a setosa iris flower. That's what we're learning here. If the petal length is greater than 2.45, now we are on this side. So then now we reach another node. This is a node. A node, or in terms of decision tree lingo, this will be called as a decision node. Okay, and then here we have 2 potential outcomes, right? So if it's true, we go here. If it's false, we go here. Okay, so if the petal width is less than equal to 1.55, then we reach to this node right here, and then there is another condition here: petal length is less than equal than 4.85. If it's true, this is the decision, right? The predicted class will be versicolor. If it's false, then this will be the prediction versicolor. So then in this case, as long as the petal width is less than 1.55, the predicted, in some sense, the predicted label will be versicolor, because it doesn't matter if the petal length is less than or greater than 4.85. Now let's go on the other side of the decision node. So here we have, if petal length is greater than 1.55, so we're here, right? So then here we have another decision node. So then we're looking at the petal width. If it's less than equal to 1.7, so then the predicted label will be versicolor. Or if the petal width is greater than 1.7, now the predicted label will be virginica. Okay. What we see here at the bottom, this node, these are referred as, and also including this one right here, those are referred as leaf nodes. Okay. All right. So those are the leaf nodes. Those are the ones that basically they have the decision or the final prediction associated to the model. Another important concept when it comes to decision trees is the depth of the tree. Okay, the depth of the tree, basically that is just the number of steps that takes you from the root node to the leaf node. So in this case, right here we have from, let me change the color here. So there is one step, 2 and 3. In this case, the depth of these three, it will be equal to 3. Okay. When it comes to building decision tree models, depth is going to be a very important concept, and that's one of those hyperparameters that you need to be very careful with, because if the depth happens to be a large number, there is a chance that you may end up overfitting the data. Okay, so depth is a very, very important hyperparameter when it comes to decision trees. Okay, so now that we have more or less an idea of what a decision tree is, how it looks like, right? Obviously we can easily see what's going on with the decision tree, right? We only, once we get to a decision node, we know that there are two options, either left or right, and then we can get to the bottom of the tree. Now let's briefly talk about how this splits, because at the end of the day, right, each of the rules behind the decision nodes, right, in this case 2.45, 1.55 and so on, there has to be some explanation where the 2.45 came from, where the 1.55 came from, and so on. Okay, so let's talk about that. Okay, so then the idea is very simple. Okay, so let's imagine a very simple scenario in which we have only two variables denoted by x1 and x2, for example. Okay, and let's assume that here we have our data represented by these green dots, or these, excuse me, these gray dots. So the idea of the decision tree is just basically, again, is just to split up the feature space into rectangular space. Okay, but it's not just a random split. Okay, there has to be some reasoning why we are deciding to split here and not here, and so on. Okay, and this is the basic idea of how those splits are made. Okay, so for example, right, when it comes to a decision tree, right, with two variables, right, so we have x1 and x2, right? So without having any knowledge about what this model is, right, someone will say, okay, maybe I want my split to be here, right? I don't know anything about machine learning, I don't know anything about decision tree, I want that split. Maybe someone else can say, okay, what about this split? Okay, and let's assume that that is a straight line. Or maybe someone else can say, what about this split? And someone else can say, what about this split? And then someone else can say, what about this split, right? And in fact, there are just too many options, right? Too many options. There has to be some sort of rule that can help us to decide out of what is the best split out of all those possible options. Okay, so let's consider the case of regression, just to make things simple, right? Regression. Okay, so Again, let's go back to our chart. So we have x1 here, x2 here. So here we have our data points. Again, so then what we're looking at here are different data points, right? So each of those data points have a corresponding x1 value, an x2 value, and they also have a y value, okay? Now, again, if you want to start splitting up the feature space, there are too many options. However, there has to be a clear rule that can help us to, decide which of those options is the best. Okay, so in the case of regression, right, meaning that the target variable is a number and we want to predict the number, so the idea is the following. Okay, so we want to select the split so that the mean square error of the data values to the left of the split plus the mean square errors of the data values to the right of the split, when you add those two quantities, is minimized. Okay, so basically is, again, for example, let's say that this is the split. So we will select the split here, for example. Okay, let's call it S1. So then the idea about selecting S1 is when we look at the data points to the left of the split and we compute the mean square error. Okay, so and what I mean by the mean square error is, think of the following. So then each of these data points have a value, right? Y1, Y2, YT, Y2, Y3, Y4. Let me rewrite this. So Y3, Y4, Y5, Y6, Y7, and Y8. So we have 8 points. When you look at the mean square error of those 8 data points, okay, and then here you look at the, now we are looking on the right side. So here we have Y9, Y10, 11, 12, 13, 14, 15, 16, 17, and 18. So when you look at the mean square error of the data points to the left of the split, and when you look at the mean square error of the points to the right of the split, you have those two quantities. So and when you add them up, that final quantity is minimized. Okay, so at the end of the day, this is just an optimization problem. We want to select the split so that when I look at the mean square error to the value of the values to the left of the split, and when I look to the mean square error of the values to the right of the split, when I add those two quantities, that final value is minimized. And that's basically what most of the machine learning models, and in general, what most sophisticated models, what they do at the end of the day is either going to be a minimization problem or a maximization problem. Okay, so let's write that out. So the goal is, let me use blue here. The goal is to find S1 so that the mean is, let's call this area here is, for example, let's call it I don't know, S0 and S1. Okay, so the goal is to find S1, which is the split S1, so that, oh, let me go back, so that the MSE of ifs, what do I call that? The MSE of S0 plus the MSE of, well, let's call this, instead of S1, just to make things more clear, let's call it S2. Okay, so then the MSE of S2, or the area to the right of S1, is minimized. Okay, that is basically what it is. Okay, so it's just finding the split, so that in the case of regression, again, we want to minimize the mean square error of the points that fall to the left of the split. We plus the mean square error of the points that fall to the right of the split. That's basically it. Okay, now this is just for one split, but in general, so let's add another page here. Let me see. New, hold on. So at the end of the day, right, or in general, right, in general, a decision tree is gonna look like this, right? Again, let's start from scratch again. So let's say these are our data points. So then, and then you start with the splits, right? Let's say you have one split here, and then another one here, and another one here. Probably, let's say, another one here. So let's say we have those 4 splits. Okay. The goal is, okay, once the splits are defined, is we want to use that information to make predictions. So for example, so if I have a new data point, right, I'm interested on predicting what should be the value associated to that new data point, and let's assume that that new data point falls here. That's my new data point. And then in that case, I know that in that specific area, I have 4 points. Excuse me, I have 5 points that I can rely on in some sense, right? So I have this point, this point, this point, and this point, and this point. Okay. So then the idea will be just to look into what are the target values associated to those 5 points and take the average. And that will be the prediction for the new point. In the case of classification, right, you look at what are the classes associated to those 5 points, and then you can easily identify likelihoods, right? So then you can estimate what is the likelihood that is this label or that label based on that information that you have on in that rectangular region, basically. And that's basically what a decision tree is. It's just splitting up the feature space into rectangular areas, so that by the time that you have a new data point and you identify in which rectangular area or in which rectangular region that new data point falls in, you can use the information that you have on that rectangular region, right, in terms of, you know, what are the data points that fall there, and use that information to make a prediction. Now, one thing that you need to be careful, especially when it comes to decision tree, is that the more splits you start making on the feature space, the more likely you are to overfit the data. Okay, so that's something very, very important, because you can keep splitting this area, right, until every single data point falls into just one rectangular area, right? And then at that point, you may think that you found the perfect model, but then what the reality in that case is that you overfit the data. Okay, you don't want to be in that scenario because overfitted models, they perform really well on training data, but they perform really, really bad on new unseen data. And the goal of building models or building machine learning models in general is you build a model that can use historical information to make good predictions into new unseen data. That's basically the goal. Okay, so you don't want to be in this particular scenario that you're overfitting the data. Okay, so you, in some sense, you need to control the depth of your tree. Okay, and that's a very, very important parameter that you need to be aware of, especially when it comes to decision tree models. Okay, all right, so then that's basically the idea behind decision trees. And when it comes to, again, the example that we just went through is related to regression, and it's very common to use the mean square error to decide where you're going to have your split. But in the case of classification, you may use other measures. A very popular one is the Gini impurity, and that's the default value in scikit-learn. However, that's not the only option. You can also rely on the entropy. Okay, so those two are measures that in plain English they will give you insights in terms of how well the classes are separated in some sense, right? So yeah, so but those are the two common options, especially when it comes to decision tree for classification purposes, Gini or entropy. Which one is the one that you need to use? I don't know. Okay, in some cases Gini is gonna be the one, but maybe in other cases you may need to try the entropy, and in other, yeah, and then probably the entropy may yield better results in those cases. So it's just, again, deciding between Gini impurity and entropy. I mean, that's another hyperparameter, talking in terms of machine learning modeling. So that's another hyperparameter that you need to tune. All right, so then that's just basically the idea behind decision trees. Now let's briefly talk about application of decision trees in data science. So decision trees, again, is one of those old school models that I think it was developed back in the idea was developed back in the 70s, but the formal paper with actual, computer implementation, I think it was published in the it was either early 80s or mid 80s. Okay, and it's being applied on many different applications. Okay, customer segmentation, credit risk modeling, medical diagnosing, churn prediction. What are the advantages of decision tree models? So number one, they're very easy to interpret and visualize. Okay, and this is a really nice advantage, because when you're building machine learning models, not all the models are gonna be or not all the models that you consider, you are gonna be able to visualize them. Okay, and also, decision trees, they have that natural flow. The natural flow structure built in that that allow others to understand what's going on behind the scenes in some sense. Okay, another nice advantage is it can handle numerical and categorical data, so meaning that you can use it for classification purposes and for regression purposes. You don't need to scale the input data, so having inputs on different scales or different range doesn't matter when it comes to decision trees, and that's a really nice feature. Okay, and it works well even when you have non-linear relationships, and this is a really nice advantage, especially when you compare decision trees with with linear models such as your standard linear regression, rich regression, or lasso regression. What are the disadvantages associated to decision trees? Number one is, if you are not careful enough, you may end up overfitting your data. Okay, so you need to control for the depth of the tree. The deeper the tree is, the higher the chances are that you are overfitting the data. So then the depth of the tree is a very important hyperparameter that you need to tune. Okay, so going back to the original chart that we have here, right? So in this case, the depth is equal to 3 because it takes us 3 steps from the top of the tree to the bottom of the tree. That's the number of steps that takes you. That's basically the depth of the tree. The higher that number is, the higher the chance, the higher the chances are that you're overfitting the data. So you need to be careful with that. Okay. All right. Another big disadvantage is that small changes in data can lead to completely different tree. Okay, so meaning that a decision tree is very, very sensitive to the input data. It doesn't have to do with the scaling the data, but then one minor change in the input data can lead to a very completely different prediction. Okay, so basically the decision tree has a high variance. That's basically what that is telling us. Okay, yeah, given how the trees are built, so greedy nature may not yield optimal global trees, is less accurate than ensemble tree models like random forest or gradient boost. Okay, but again, to me, this one right here is an unfair comparison because random forest and gradient boosting trees are built on top of decision trees. Okay, so to me, that's not a fair comparison. Okay, but in future tutorials, we will talk about random forest and gradient boost. Okay, in conclusion, decision trees are a powerful and interpretable tool for supervised learning, meaning that we have a specific target variable that we want to model. While they can overfit, especially on noisy data, they can provide a strong foundation for a more advanced ensemble models like random forest and gradient boost. So there are a very fundamental piece, especially when it comes to predictive modeling in machine learning. Okay, so once again, in future tutorials, we will talk about random forest, we will talk about gradient boosting, and you will see that they rely on single decision trees. Okay, all right, so that's all I have for the notes. Now it's time to write some Python code. All right, guys, it's time to code. So now we're gonna go over this simple example that will highlight how you can build a decision tree model on your data. Okay, so once again, we're gonna be using that bankful.csv data file just for illustration purposes. Just to give you a quick reminder about what this data file is about. So here we have some basic demographic information on bank customers. So there was a marketing campaign that it was run for a period of time in which the marketing department of this I think it was like a European bank, So the marketing team ended up reaching out to the bank customers, and the goal of that interaction was just to see if the customers were interested in enrolling in some sort of like a special direct deposit program. Some of them they ended up, you know, enrolling in that program. Most of them they decide not to do that. So you know, in terms of machine learning, so we have all of these variables, right? Age, job, marital status, all of that, up to previous and outcome. So we will use all of that as input data, and the target is whether they decide to enroll in the program or not. Okay, but yeah, so in this particular exercise, we're gonna be using this data file, and we're gonna be building decision tree models on top of it. Okay, so let's run this. And again, so then we already seen this on the previous tutorial. So then just to get an idea about the distribution in the data. So y is the target variable, and we can easily see that, roughly speaking, 88% of the data has a label equals to no. And roughly speaking, 12% of the data has a label equals to yes. Then after that, we define the input, which is very common to use X as a label for inputs in machine learning. For the target, it's very common to use Y, and we know that Y, the values stored under Y are labels, right? No and yes. So what we're doing here is we're mapping no to zeros and yes to ones. Okay. And then the next step is, again, looking into the data. Some of those variables or some of those features, they have categorical information stored in it, right? So job, so we have management, technician, and so on. So then that's label data, right? Same thing for marital, same thing for education and others. So the reality is that when it comes to building models, we cannot build models with labels. So we need numbers, basically, okay? So we need to pre-process that information, right? That label information, and we will map those into numbers by using the ordinal encoder function, which is part of scikit-learn pre-processing. And that's what we're doing here, okay? So when we run this here, so then now we see that, again, a job used to be labeled, right? Management, technician, and so on. And now we see numbers. So for example, management, it got mapped to 4. Technician, it got mapped to 9, and so on. Okay. All right. So then the moment that you have the data as numerical or as numbers, so then at that point, we're ready to build our decision tree model. So we're going to start as follows. So first, let's build a model, or let's load the command that we need to use to build a decision tree model. And that's going to be part of scikit-learn. So import decision tree classifier. Okay. So let's define the model, and let's use dtmd equals to decision tree classifier. Let's use the following. So max depth, which is the number of steps that takes us to go from the top of the tree to the bottom of the tree. So let's use 3, right? Because I want to visualize this so you can see more or less what's going on. So random state equals to 42. So up to that point, I define the model. Then after that, I'm ready to apply that model to my data. So fitting the model. So dt.fit x comma y. So then that fit command is gonna use that data. What data? So x, the inputs that we define here, and the y is gonna use it as a target variable, and that was also defined here. All right. So up to that point, we define the model, we apply the model to the data, and let's visualize the model, because that's one of the nice features associated to decision trees. You can visualize the model. Okay, so visualizing the tree. So the command that there are two important commands that we're going to use here. We're going to use plot tree, which is part of the tree sublibrary, and then we need matplotlib. Okay, so then once we load those, so then here we're defining the size of the figure, and then plot tree. And then the first thing that we need to do is to enter the model after the model is being applied to the data. And then the names, so the columns, the classes, field. And then we're just running this. Okay. And let's add a title, PLT title, decision tree visualization, and PLT show. Okay, here is the tree. Okay, so it's a simple decision tree. Again, here at the top. So here we have the root node. Here at the bottom, here we have the decision nodes. Okay, so because we specify that this is max step equals to 3, so it takes us 3 steps to get to the bottom, from the top of the tree to the bottom of the tree. So 1, 2, and 3. Okay, again, I'm assuming that if the duration is less than, I think that's 521.5. If that is true, we go here, and if this condition is true, then we go here, and if this condition is true, we go here, and that's how you get from the top to the bottom. Okay, and it also, the nodes, it tells you what is the predicted class, right? If you fall in this node, the predicted class will be no. Here it will be no, no, yes, no, no, yes, and yes. Okay, so again, this is just one of the nice features associated to decision trees, that you can easily visualize the data, and you can see you can easily visualize the model, and then you can see what are the rules behind the model, and it shows you in some sense step by step how you can reach a particular prediction. All right, but then now, given that this is just a machine learning tutorial, so let's start running cross-validation experiments. Okay, so let's start running a cross-validation experiment. We're gonna use 5 faults, and let's evaluate how good this model is at predicting the target variable. Okay, so from scikit-learn model selection, so the two commands that I always use, especially in classification, is stratify k-fold. Again, that will ensure us that as we're splitting the data into folds, that the proportion of zeros and ones are more or less the same. Okay. All right, so let me just double check something really quick here. All right. And cross-valid score is just to run the cross-validation experiment. I already load the decision tree classifier, so I don't need to load it one more time. I think that's all I need. So defining the model. So I'm gonna call it DTMD. So as the initial experiment, I'm just going to use default values. Okay, and then defining the cross-validation method. So I like to use skf for that. So on stratify k-fold, 5 folds, random state 42. And then now here we're going to evaluate the model using cross-validation. So let me call this DTCB. cross-value score. So first we enter the model, then we enter the input data, the target, the cross-validation strategy. Let's use, just to keep things simple, rock AUC as the measure of performance, and jobs equals to -1. Print. All right. Okay, so again, we're using just a single decision tree, and we're using all the default values. Okay, so let's run this. All right, so the overall or the average 5-fold cross validation using the AUC ROC as a measure of performance basically is just 70%. Now, what do we know about the AUC ROC is the closer that number is to 1, the better the model is at predicting the target variable. Okay, so now let's see if we can do anything to make this number better. Okay, so let's copy this basically. Okay, and let's try different depths. Okay, so I don't need to rerun the split because that is already been defined. What I'm going to do is now I'm going to start playing with the depth of the tree. So let's use max depth equals to 3 now. Let's see if that helps. Okay, let's run this. Okay, look at that. So then initially using all default values, we have a 70% AUC ROC score. Now the max depth is equals to 3. Now we have pretty much a 79% ROC AUC. So that's a significant improvement. Okay. All right. Now let's keep playing with that hyperparameter. Let's see if we increase that to 5. Hopefully we will get better results. All right, and then we are lucky. So now we're using max step equals to 5. Now we get 84.72. Okay, let's keep going. And now instead of 5, let's use 7. 87.38. Okay, so the moral of the story here is, again, here we start using just default values. Okay, and this was basically the benchmark that we want to beat. Then we start playing with the max depth. We went from 3 to 7, and then we notice a very significant improvement. Okay, so the moral of the story here is that max depth is a very important hyperparameter when it comes to decision trees. However, you need to be careful, because not because you can increase that value that you should do it, because the larger that value is, the more likely you are overfitting the data. And overfitted models, they do not generate good predictions. Okay, so always keep that in mind. Okay, so once again, this is just a very simple tutorial that shows you how you can build a decision tree model or a decision tree classifier model on your data set, how you can easily visualize it, and how you can run cross-validation experiments with it. Okay, so that's all I have for this tutorial. Once again, if you find value out of this video, like and subscribe. Well, yeah, that's all I have for this one. See you on the next one.